I actually lied to you in the last video, so the final equation I presented to you was not quite right. So, remember we had something like this. Let's see, the CNF alpha, the aerodynamic center of the fin, center of gravity, and times alpha, and the term of the body. So this equation is not quite right. And somewhere in here the damping terms are going to pop out. Let's see where they come from. So awesome, I've just discovered how to do straight lines. So imagine we have the roll axis here. So this we'll call roll axis. And oops, sorry. Let me get this out. Bye. I have to remember to disactivate this. I'm sorry for this. So, and then the rocket is at a certain angle of attack. So the rocket axis is at a angle alpha with the roll. No, sorry. The incident wind is at a certain angle with the roll axis. Okay, so let me draw it. Okay, so this is the wind. So the incident wind. Incident. So V will be in this direction. Alright. And this angle then would be alpha. We'll put the center of gravity here. So what's the rocket going to do if it's at a certain angle with the incident wind? Well, it's going to stabilize. The roll axis is going to try to align with the incident wind axis. Doing that, it's going to induce a certain angular acceleration and an angular velocity. Then, if we take a look at what's happening in the fins, for example, we have their aerodynamic center here. Well, the rocket is moving. It's at an angular velocity alpha dot. So at this point, at the aerodynamic center of the fins, well, we have an induced velocity. We'll call it velocity of the fins, which is equivalent to the following. It's simply the angular velocity times this distance, which is sorry, it's not the XAC, but it's the aerodynamic center of the fins minus the center of gravity. So it's this times this. Cool. So what happens is that the velocity that the fins see is not actually v, but it's v. Let's put it down a bit. That'll be good. The velocity that the fin see is v plus this VF. All right. So this angle here, we'll call it the geometrical angle of attack, which is defined as the angle between the roll axis and the incident wind axis. However, what the fins are actually seeing is another wind, because we have to add this velocity to this velocity. So let's take this V out of here. It's kind of disturbing us. Cool. So we have to add that's terrible. Okay. So let's see. This is V, and okay, the geometrical angle of attack is this. So, but the angle of attack that the fin see is not alpha. It's not the geometrical angle of attack, but it is the following. It's this angle here, which we'll call alpha fin. If we take let's do, for example, the tangent of alpha fin, it's going to be equal to the, let's see, the sine of alpha times V minus VF, and divided by the cosine, well, V times the cosine of alpha. If we do a series expansion for the tangent of alpha at small angles of attack, tangent of x is it's x plus x to the third, I believe. Then, well, higher order terms, but we're only gonna take the first term because we're gonna always talk about small angles. So, and because we're discussing small angles, well, the sine of alpha is just going to be alpha, and the cosine of alpha is just going to be 1. So then we have, and then before we said that the velocity, the induced velocity due to the angular velocity at the fins, this is just equal to the derivative of alpha, this. So now you can see that the angle of attack that the fin see is equal to this. Alpha minus, let's see if, okay, and divided by V. Okay. So the thing I lied to you before is that in this equation here, we don't have alpha. We have the, let's say, the alpha that the fin see and the alpha that the body sees, which is different alphas because, because the body is at another location. So if the rocket is rotating this way, well, the relative velocity is going to be different. Okay, it's at a different distance from the center of gravity, which is the point at which the rocket rotates. Okay, so the thing that was wrong in the last equation is that here we left this, and this is what we just developed before, just a minute ago. Is this? I don't care much about the signs of this. We could just we could just think that a positive alpha dot reduces the alpha of the fin, so it would actually cause what's a bit look, never mind. I'm just gonna write down the final, well, not the final still, but the corrective, the corrected equation, the angular equation of motion is gonna look like something like this. Alright. Alpha times. So I just substituted this on the other equation, but note I did a little change with the signs. Again, the damping is acting, let's see, against the increase of the of alpha. It isn't. I mean, it isn't the best explanation, but I'm just trying to explain like quickly why this is positive. Well, it's going to be positive in the final equation, but if not, just believe me. And I'm gonna go ahead and present to you not the final, but a new version of our angular equation of motion. Which again, I'm going to lie to you because I left out some terms, but still it's going to look better because finally we have something that depends on alpha dot, which is the first derivative of alpha. And this term, the things that go along with the first derivative of alpha are going to be the damping terms. So finally we do have damping terms. It looks way much better. Let me first finish this off before further discussing it. So we have the terms that say the first order, the zero order term, so that go with alpha, times the terms that go with the first derivative. So we're just substituting again this on our old equation. Oops. Sorry, I just realized I put x of the fin here. Obviously this is the aerodynamic center of the body, not of the fin. Cool. Oh, this is squared, of course, because we're multiplying twice, yeah. And then we have the body term. So the body term b cg squared. I'm going to leave a space here because I put everything on the same side, so I'm going to leave a space here because I'm leaving out one more term I'm going to talk about, which is also going to be a damping term. So we have damping terms that come from the oscillation of the rocket. As you can imagine, this damping term is going to be minuscule because, yeah, how big is this velocity going to be compared with the incident wind velocity? It's going to be tiny. So that's why rockets are going to be really undamped systems, as we can see in the next video. So rockets are really undamped. However, I told you there's one more damping term, which is not related to aerodynamics, but it's caused by thrust. So there's thrust damping also. And as the name might suggest, there's only thrust damping when there's, well, the thrust of the rocket, when the motor is firing. So the thrust damping term is going to be this term here. I'm going to add. And the thrust damping term is proportional to the mass flow rate of our rocket motor, which is something we're going to discuss in section 3, which is about solid rocket motors. The length of the rocket minus the center of gravity divided by dynamic pressure and the reference area. So this looks much better. We have now damping terms, which were the ones we were missing, and what this differential equation describes is a damped oscillation. So it's equivalent to having the same system I described before, a mass attached to a spring but with a damper. Okay. So let's see. If you're not familiar with, well, I'm gonna look into this in the following video. So I'm gonna explain to you what this equation means in terms of, what's buried behind this equation. What this is. It's a second order system. And what's it going to do? It's, if this is alpha and time, well, it's going to oscillate. If we give it a kick, okay, it's going to oscillate, but in a damped, in a damped way. Okay, so the damping is going to hopefully fade away the perturbation, and is going to cause the rocket just to go back to alpha equals 0. As I said, rockets are really undamped, as we're going to see. We're gonna see how much, specifically how damped they are, but you're going to see that really undamped. This means that it's going to oscillate a lot, theoretically, until the perturbation just fades and dies off. So in the next video, I'm just going to discuss what are second order systems like, and how do they behave, and try to model all this behavior in front of perturbation.